Welcome back to Computer Science 305. This is the second part of the concurrency lecture. And so in this part, I want to talk about more about Java and threading. And so in order to do that, I think the best is to look at some example code that I wrote, borrowed from other people. So and we talked about using the thread class by itself, and I suggested that that was probably not the best way to go. And really, most of the time, what you need to do is you simply need a runnable. For the most part, there are four classes really that, or four interfaces that you can utilize to provide you with the necessary components to construct a threadable or concurrent components to your actual system. And so those are the runnable interface, which provides a single method run, which is where your multi-threading code goes. Callable, which I believe provides the call method, which returns some type. So callable is a generic type. I believe we can actually look that up really quick. So if we look inside this actual interface, it's the callable takes in some generic type v and then provides a method called call that throws returns a type v. Similarly, if we went and looked at the runnable interface, we'd also see that it provides the run method and returns void. So these two components are the basic components of a threading instance, right? Runnable has been around since JDK 1.0, while callable has been in existence since 1.5. So, all very good. Now, the interesting thing about all this, right, is that in order to make callable work, we have one other piece, which is called a future. So let's see if I can't go and find one of those. I believe it's in here. So let's see, future. So a future is another type of interface, right, that has a bunch of different things, but a future just is a representation of the result, the future result of some thread's execution. And so it typically returns a type you can call get, and note that when you call get, it forces the thread that's calling that to wait until the computation is complete and to retrieve its result. If the computation is already complete, it instantaneously returns the value. And no, there's a whole bunch of different exceptions that can be thrown along here. You can also call get with a timeout and a specific time unit, which can be one of the like nanoseconds, microseconds, etc. But you can also cancel a job. You can check if something is done. You do a lot of different things going on here. And there's a lot of ways to utilize this. But we'll talk about that one as well, along with the callable. And then there's two others that we'll talk about after we sort of run through runnable and callable. So the runnable, basically I wrote this, there's this simple class, and I'm going to run it really quick so we can see what it does. And this is the bouncing ball, right? So we have this, we want to create a user interface that simply just bounces a ball around for a given number of steps, which in this case is 1,000, and has a delay right now of 5 milliseconds. And so if we press start, each time we press start, it creates a new ball, and each ball is itself a thread, right? And so how that works is, essentially, in that UI, we have a JFrame, right? And we have that add button. So every time we click add, that's going to call this, apologize. Every time we call that, it's going to, when we call add ball, it's going to create a new runnable of type ball runnable, right, which takes a ball, which is the one that we create here, and a component, which is the canvas on which the ball will be drawn. And it's going to stuff that runnable inside of a thread and then call that thread.start, right? So if we actually look inside the thread method, thread takes a runnable, so you can create a new thread by itself and then it just initializes nothing. But normally what you want to do is give it a runnable on which to execute. There's all sorts of different ways you can do it. You can name threads, you can do a lot of different things to make all this stuff work. But the most important thing was we give it the runnable, the thing that we want to run in this other thread, and then we call the start method, right? And then the thread goes through its processing and eventually gets to the dead state and it returns, and then it's done, right? That's when the ball is finished. Now, in the run method of the ball runnable, right, which we see implements runnable, what it's going to do is it's going to walk through this for loop and simply just update the animation as it goes along. Now if we were to go and look at that one more time, I still have it running, so we can see that creates the ball bounces around and ends up where it's supposed to, right? So we can, every time we do that, we create a new one and it's all good. We already saw that. Okay, so now note that I pressed the close button and there were still balls that were in motion, right? Well, the close button calls system.exit, and that's from the main thread, and so it kills everything, regardless of whether or not those threads have stopped finished processing. It doesn't care, because we're actually killing the parent process of those threads. But anyway, so this is pretty much the gist of a runnable, and how we actually can. The simplest way of creating it is literally by using an actual thread. As I argued before, this is not the best way to do this, and so I would argue that it's better than the previous method, which was to extend the class thread itself. So that's runnable, right? So now we want to look at, maybe we want, and a runnable can never return a value. It just goes, does some computation, and then finishes. And so that's great if that's what we want, but oftentimes we actually want to have it go process some bit of data and then return a value to us. And so that's what the actual callable is for. So in this example, we have a pretty simple class that is just going to walk through and execute this match counter. What that's going to do is it's going to walk a directory recursively, looking at each. If it finds another directory, it's going to recursively call itself. If we were to do this sequentially, right? And then it goes through every single file that it finds and attempts to read it and scan for a certain keyword in the text. And so it will go through, and anytime it finds that keyword, it will return the value. It'll indicate that was one of the files it found that in. And so it'll collect up that, and it increments a counter, basically. Well, we can do this in a multi-thread way by having a new thread for every file, every folder to scan through, right? And so that's what we do. We create this class to be an instance, in implementing the callable interface with integer, right? So it's going to return the count of items it found in the directory it processed. And so instead of recursing, what we're going to do is we're going to actually create a new instance of match counter for that. So that's what we do down here. Basically, how we're going to do this is we have this concept of the future, right, which is the result of the thread that we're going to spawn finishing, and we're going to kind of jam that up into this future task. A future task is simply a class that produces a runnable future. Okay, so it's a task that we can execute, and what we're going to do is we have a whole bunch of things, but we can create a future task for a callable. So this is sort of like creating a thread, but instead of for runnable, which thread's only for runnable, we're going to create one that's for callable this time, right? And then we can do, we can cancel, we can call it as done, we can get the value of it, etc. So that's what a future task is going to provide for us. So we then can jam the future task, because it's of type runnable, into a thread. Okay. So every time we walk through, if we detect a directory, we're going to construct a new a match counter for that directory, searching for that keyword, and then it's going to add that task to our results list, which is a list of futures, right? And we're going to then jam that task into a thread and then start the thread. So anytime we detect anything else, we're just going to search the file. So once we get done processing our current set of files, we then take all those results that the futures that we collected up, and we're simply going to try to increment our actual count with the results from those other threads. So we're going to bring them back down into this one, and we're going to block on this thread until we collect all those results. So, and then once we're done, our current callable returns its actual count, right? And the search, don't worry about that. And then, interestingly enough, we have to start this out just like in recursion, right? We have to have our initializing call of that, and so whatever directory that they provide to us is where we're going to is the first thread that we spawn, and then yet again we do the same. We'll try to get that task, and that count that it provides is the sum of the counts of all other directories, right? So then we go ahead and we do the same thing. We call the thread task, and then we call t.start, and it goes long. So we'll go ahead and run this one. On the directory for the class, so that's under Git, and then we get a keyword. We'll just look for CSCI, and we run that, and it found 134 matching files, right? And it was good to go. So yet again, we did this whole thing where we kind of jammed in another, runnable basically into. Actually, I want to take a look at that. See, runnable future. Runnable future extends both runnable and future from as an interface. So that's how we can actually do that with our thread, right? So as I've been alluding to, that this is probably not the best way to do this. Mainly the problem here is the construction of threads over and over. It's not quite as hefty as creating a process, but it still does take a lot of resources to do that. And so one of the things that what we can do is we can actually have a pool of existing threads. So let's say we only need maybe, I don't know, 8, 10, 100, whatever threads, and we want to be able to reuse those. So there's this technique called a pool. It's a pool object, which then maintains a certain set of objects that we can keep reusing over and over. And so one of these, typically you want to do this when you have resources, for example, that are costly to construct, and then so an example of these would be a thread, or a network stream, or a database connection. Several of these things are actually quite difficult, not difficult, but costly to construct. And so we've created all these pools to handle a lot of these. Like there's a JDBC connection pool for databases, and then there are thread pools for threads. So this is the same thing as the matcher again, except we're going to use a thread pool. And so in order to do that, we create this thing called an instance of an executor service. And so all an executor service is, it's a type of executor, which is a thing that will construct threads for us as necessary, and then will execute runnables, callables inside of those. And so basically, there's a whole bunch of things we can do. I believe the executor, yeah, so the executor service has things like we can submit callables, we can submit runnables, or runnable tasks actually in this case. We can call invoke all, which takes a collection of callable tasks and will execute them, returning a list of futures for us to utilize. So we can do a whole bunch of things with this. And the way you construct an executor service is simply by, I have to figure out where I actually do that. It's up here. So we create an executor service by calling executors. And executors is basically just a class with a whole bunch of static methods that will construct the right type of thread pool that you need. So for example, if we just want a certain number of threads, for example, like let's say 8, then we say I want a new fixed thread pool with 8 threads, and it will fill in a bunch of details for you and constructs basically a new blocking queue of runnables that it will use to do that. We can have work stealing pool, which handles assigning. So as work is getting done, different threads will attempt to finish jobs as necessary. There's a whole bunch of these different things out there. You can also have just a single thread executor. If you only need one extra thread, you can use that, and then you can submit jobs to it as necessary. But this handles a lot of the stuff that you might need. The new cached pool, thread pool, which is the one I believe we're going to use, will construct as many threads as necessary, but we'll keep them around in order to complete jobs once they finish up. It'll keep them going as necessary. Furthermore, we also have we can use a special thing called a thread factory, which we can use to we can actually extend this to create our own method by which we construct threads themselves. Anyway, there's a whole bunch of these things down here. I'm not going to go through all of it, but just know that it's there. So we use the executors, and we create a new cached thread pool. And then now, instead of doing what we did before, which was to create our own thread, we're going to use the pool, and we're going to submit. This is for the initial start of the match counter. We're going to go ahead and submit that initial one to the pool. But we note that we added an extra argument to the match counter constructor, which is the pool that we're using to construct our threads, to add jobs to. And so what's going to happen is we come down here to the actual match counter, where we see we have the executor service available to us, and we're going to use the same type of logic down below as well. Now, every time we encounter a directory, we're going to create the match counter again, but now we're going to submit that counter and collect its future and push that into our list. So now we have this nice way of handling this. We don't have to construct the threads ourselves. We don't accidentally forget about them, anything like that. We let the thread pool manage all that for us, as we should. And so everything else works just as before. So now, when we go ahead and run this, it executes the same as it did before, and it will do quite well. I'm not going to run it for a second time. So now we've covered, basically, these are the things that we have figured out now. So we have talked about what runnables are, what callables are, futures, and now thread pools and the executor service. So these are the basics of just your standard Java threading, and we're not even getting into the use of synchronized or volatile, because all of our threads are kind of running by themselves, and they're not really interacting with each other. So we pretty much don't have to worry too much about what's going on. The only data that they're actually interacting with is data that's stored within themselves. They're not manipulating anything that is not thread safe, right? The thread pool itself is thread safe, right? So we don't have to worry about that. And so everything is pretty much interacting quite well on its own. We don't have to worry too much. All right. So that's that part, right? And so the other one that I want to look at was dealing with this producer-consumer stuff. And so well, I think what we'll do is we'll look at one other thing first before we do that, which is the fork join framework. So in Java 7, there's a design pattern called fork join. Now this is for, so the previous one we just looked at was recursive, right? We walked down a directory structure, and we we're recursively creating threads as we encounter directories. Well, in order to solve that, because that's a very common problem when you're dealing with multi-threading itself, and so what they want to do is they wanted to create a thing that allowed this to be a little more natural. So essentially you're forking threads as you need, and then you join them all together when the recursion comes back to a head, right? So that's essentially what we are doing with the callable when we call get. So they created two different classes. The first one is recursive task. Recursive task is like a callable, and it simply defines it implements fork join task. Extends fork join task, but it defines a compute method that returns some value, right, which is a generic type. And then we have a couple other things like you can get the raw results, you can set the raw result, you can call exec. But the only thing that we really want to do is implement this compute function. Now, along with in the fork join task, we can actually take a look at this, and we can take a look. There's a whole bunch of other ones that are provided, but the other main one that we want to look at is, I believe, recursive action. So recursive action is like a runnable that provides and it has the compute method, but it doesn't return anything. It just kind of is called. It will go along and do something, and then it returns nothing, right? And so once we have all that done or understood that we have recursive action, recursive task. I believe I implemented a simple little fork join test that basically we have some set of numbers, right, an array of numbers, and what we're going to do is we're going to pass that into this counter, and what it's going to do is given a threshold of 1,000, it's going to essentially check if the to/from values that it's provided, right, when we make the call. So we start with 0. Initially we start with the entire length, right? And then we have this lambda expression here, which is basically a filter that says we're going to break down by 1/2, right? So we're going to, the spread will be 1/2. And so essentially it's going to break this array down, and it's going to essentially divide it into small pieces and sort of walk through, and then it's going to count up the value, right? And it's going to continue doing this, I believe. Yes, so it's going to say if it does check to see if the filter accepts, and then it's going to upgrade the count, right? So it's just doing a count. If our if the value that we have is greater than 1/2, right? So essentially, if it's the value is greater than 0, it's going to if it's greater than, yeah, so it's a double, and then it's just some random number. So if it's greater than 0.5, it's going to attempt to increment that value, the count. So it's counting up out of the 1 million. The 10 million values that we have. It's going to attempt to count how many of those are greater than 0.5, as we state here in the filter. So once we've done that, and every single time it's going to construct 2 new counters having the size of the array that we're counting down, and and then it's going to call invoke all. And so if we look at the invoke all, right, it's going to take in, n number of fork join tasks, and it's going to essentially call do invoke, right? And then it's going to call do join, right? Which means that whoever the initial S1, S2 are the things that we're going to join to. But I'm not going to worry too much about how that works. But essentially what it's going to do, once we have that, then we're going to call join. So we're forking these two things out from where we're at, and we're going to join, which will then return the value. So join returns the value from the recursive task that we called. And then what we're going to do is add those two values together, and we'll return that. Otherwise, if it's less than our threshold, which is 1,000 in this case, we're going to simply count those up. Pretty easy day. All right. So now, if we go ahead and run this, it should just come up with a quick number. So we took almost no time to go through 10 million items, right? If we were to do that straight up, it would take quite some time. So it counted up, what was that? Looks like about 5 million. So about half were were greater than 0.5, which is to be expected in a uniform distribution. Okay, so the final one is a producer-consumer concept. So in this, we have two runnables, and one produces and one consumes. And so the concept here is that this is where we get into cooperation synchronization. Where essentially we need to communicate. And how we're going to communicate here is by using a transfer queue. And note that there's no synchronized anything here, because nothing that we're doing in the producer, right, has anything to do with the consumer. They're not interacting with each other. They're interacting through this transfer queue. And so transfer queue is a type of blocking queue. And note it's in the java.util.concurrent. So it means we know that this is thread safe. A blocking queue is simply a queue that what it does is it prevents any access. It blocks any access to it unless from anytime one of its methods are being called by a single thread. It blocks all other threads from using the rest of the methods. So specifically, when we are working with an actual read or write, so we're asking what's in the queue or we're adding something to the queue. In the transfer queue, we have a couple of methods that we really want to work with. The first one is transfer, and the second one is, I think that's the only one. Yeah, that's the only thing that we have. So what transfer basically transfers an element to a consumer, right? Waiting if necessary to do so. So I believe we can go back and take a look at this. So the consumer, right? So both the consumer and the producer take in a transfer queue, the thing that they're actually going to use to communicate, which is provided by the base class producer consumer, which in this process method creates the actual transfer queue and a new fixed thread pool of a certain number of threads that provide, and then we have two producers and two consumers, both which gets the transfer queue and have their own names, 1, 2, and 1, 2. Anyway, so using this, we can then we execute each one of those. So now they're at this point in time they're running, and then what we're going to do is we're going to await termination, right? So this executor service, we're going to say we'll await until all the existing queues, not queues, but all the existing threads are complete, and then we'll have a timeout of 5 seconds, right, on which this termination to detect when termination has occurred. So if we look at this, it says blocks until all tasks are complete execution after the shutdown request, or the timeout occurs, right? So this is going to block until we've reached that timeout after a shutdown call has occurred. So once this occurs, so it's going to block here, and then we call shutdown. Shutdown just shuts down the executor service and then continues on about its business. So when the producers are running, they're essentially going to just create a bunch of messages, and when they create them, they're going to try to transfer. So they'll attempt the transfer, and then once the transfer is complete, right, with a timeout of 4 seconds, they will then increment and get, right, so an atomic increment, the message is produced. So as we can see, here's an atomic integer. Similarly, the consumer will, in its run method, go through it has a certain number of jobs it can actually process. It will then take from the queue, right, and then it will update, update the UI. And then it executes this long processing. All that does is it just increments and gets the jobs consumed, and then sleeps for, in this case, 50 milliseconds, right? And then that's it, right? So both of them update the actual, only this one updates the actual UI counts of messages that have been consumed. And it will know which one is updating from. So if we go over to the actual visualization, we just have basically a simple UI, which I'll run right now. Alright, so in this we have blue for producer 1 and red for producer 2, and then our different consumers. And so this value is the number of things that consumer 1 can consume, and this is the number for what consumer 2 can consume. And then this is the number that are produced by producer 1 and number produced by producer 2. And then we're operating with 3 threads. So if we go ahead and start that, and we can see that it runs pretty much as we would expect. Now if we update this, let's reset, actually update that, and we start this, so it will produce 15 overall, right? But from consumer 1 will be able to consume 15 items. Consumer 2 consumes up to 10, but we only produced a total of 20, so consumer 2 is just sitting there waiting. We can continue this all day long. It's pretty simple. It's just to see that we can actually do this in real time and update things as necessary. Now if we look though, if I go ahead back to our visualization, I believe I may have seen, so our update method here, I actually had to call this synchronized because this is potentially being updated by 2 different threads, which could, given that it's sending in an element and a connection and the name of the consumer, it can actually cause errors if we don't synchronize this, because it will be trying to do too many different things and will overwrite the values of C and P and possibly the producer here. So we want to ensure that that doesn't happen, so we use the synchronized keyword to limit access to this to only 1 thread at a time. Once we're done with that, that's the only thing that needs to be synchronized, because it's the only thing that's accessed by our outside threads. Furthermore, it's the only this is a singleton class, and instead of using double check locking, we used a holder class with a get instance method that allows it to be thread safe while simultaneously lazy evaluated. Anyway, so this code will be online for you guys to go check out, and I hope that you don't have too many problems. If you have any questions, please stop by during my office hours.